Dear learners, last time I mentioned the etiological classification of aniseikonia, and I discussed the most important cause, which is the optical one. And in this part, I'm going to start talking about the retinal cause. So retinal cause or retinally induced aniseikonia, sometimes it's called anatomical aniseikonia. So in short, it is aniseikonia due to difference in the distribution of retinal elements. Here I mean by retinal elements the visual photoreceptors, in which wide separation of visual elements will result in small perceived retinal image, or we can call it micropsia. On the other hand, narrow separation of visual elements will result in large retinal image or micropsia. What about the etiology for retinally induced aniseikonia? So it could be due to retinal asymmetry in the axial lens. If we have a high axial myopia in one eye, there will be stretching of the photoreceptors, so the retinal image will fall on smaller number of photoreceptors, resulting in micropsia. Or pathology, such as epiretinal membrane. So epiretinal membrane can cause micropsia because of the contraction of the membrane. So the photoreceptor will be compressed, so the retinal image will fall on a larger number of photoreceptors. While macular edema or CSR, short for central serous choroidiopathy, due to fluid accumulation, so we will get wide separation of visual elements, and this might result in micropsia. In summary, if we have a retinal asymmetry or pathology, this might cause that the same physical size retinal image to be captured by a different number of photoreceptors, resulting in change in the perceived image size and sometimes shape. Now, let's revise some very basic optics facts regarding the factors affecting the perceived image size or the apparent size of an object. In this schematic representation, here we have two objects. Both are located at the same distance from an eye. But we have here a small arrow, the gray one. So the retinal image formed by the gray arrow, suppose it stimulates 5 photoreceptors, while the larger arrow here, the red one, stimulates, let's say, 10 photoreceptors. And as you can see here, the retinal image formed by the smaller object is smaller than the retinal image by the larger object. And this is the factor number one that will affect the perceived image size, which is the size of the object in the space. So how about the second factor? Here in this diagram, we have only one object, which is the gray arrow. At this distance, it stimulates 5 photoreceptors. How about moving this arrow closer to the eye? Now, if we draw 2 rays from the extremities of this arrow to form what's called the visual angle and to draw the retinal image. So as you can see here, the retinal image now stimulates larger number of photoreceptors, let's say 10. So we will get a larger perceived image. So the second factor that will affect the perceived image is the location of the object from the eye. And of course, closer the object to the eye, the larger the image will be formed. Another related concept here, if we have 2 objects, one small and the other one is larger, but the larger object is located far away from the eye. And as you can see here, both objects somehow created the same visual angle and both created the same equal retinal image size, despite the fact that we have 2 different sizes. But because the smaller object located closer to the eye, somehow both created the same visual angle and created the same retinal image. In fact, this principle has many applications in our daily life. So if you are holding a coin at arm's length from your eye, you can obscure the view of a huge distant object like a moon, because both are created the same visual angle. And since the coin is in the path of the rays from the moon, you can obscure or hide the view of the moon. Let's revise an important definition in optics, which is the visual angle. So it's the angle formed by the 2 lines drawn from the extremities of an object through the nodal point of the eye. So the nodal point is simply closer to the posterior pole of the lens. So as you can see here, We have different sizes, but because of different distances, all have created the same visual angle, and both have all have the same retinal image size. So the apparent size depends, number one, on the visual angle, which depends on the object size and distance from the eye. The second important one, which is closely related to our topic, which is the photoreceptor density. So let's discuss further about how the photoreceptor density will affect the perceived image size. So this is a schematic presentation of how a change in the receptor distribution can change the perceived image size. If we have an object arrow here, located at a specific distance from the eye, and this is the inverted arrow on the retina. And this is just a representation of the photoreceptors. Note that the receptors here are drawn in form of equidistant rectangles, but in reality, of course, the distance between receptors vary. Suppose this retinal image stimulated like 6 photoreceptors. And now the eye developed a retinal membrane, in which a contraction of membrane compresses the photoreceptors. Now this image will stimulate a larger number of photoreceptors, and this will result in that the perceived retinal image will appear larger than it should be. So we will get micropsia, or magnification of the image relative to the other normal eye. And here is the opposite. Suppose this eye developed macular edema. So here the image will fall on fewer number of photoreceptors, and this will result in micropsia. So the perceived image will appear smaller than it should be. Collectively, micropsia and macropsia both are under the heading of a term called dysmetropsia. So dysmetropsia, it means having either macropsia or micropsia. And this is a clinical example of a patient taken from this reference. So this is an OCT of the retina, and in a case with macula on retinal detachment, here I delineated the epiretinal membrane. And as you can see here, the authors documented that she developed about 4% of macropsia because of this epiretinal membrane. Another piece of advanced knowledge here, there is something called field-dependent aniseikonia. So let's try to simplify this schematic representation taken from this reference. We have two images, retinal images, big one represented by the red arrow, and smaller image formed by a smaller object in the space, which is the green arrow here. So normally, there is somehow of normal distribution of photoreceptors. I counted the rectangles here in this schematic representation, and let's say they are 10. Now the eye developed a pathology which causes altered receptor distribution. But as you can see here, the alteration is not uniform. So we have much compression or much crowding of photoreceptor in the center here. We will get a larger number of photoreceptors to be stimulated because of this crowding. So both images of those two objects will perceive the larger. So we have macropsia. But the smaller arrow, the macropsia of the smaller arrow is much bigger than the macropsia by a larger arrow, because the smaller arrow here is falling on the area of greatest crowding, while the red arrow fall in an area where there is no crowding here. It's almost stretching or normal distribution of photoreceptors. To sum up this, we have a change in the receptor distribution that is not uniform, and this results in what's called field-dependent dysmetropsia. The last point in this presentation, we have both. Sometimes we have combined mechanism for aniseikonia, retinal and optical. So let's see this example we demonstrated last time. So this is a case of high axial anisomyopia. And as we discussed last time, this is a case of optically induced aniseikonia, but because of high myopia in the right eye, and stretching of the photoreceptors due to elongation of the eyeball in the right eye, you might expect that there is some kind of retinal anatomical aniseikonia, and sometimes we call it inherent. So this is an example of both mechanisms that might cause aniseikonia, retinal and optical. Now we've completed the two major causes of aniseikonia, and still there are two other causes to be discussed in the next part. Thanks for watching. I'll see you in the next video. Take care. Bye-bye.